Hey everybody, let's get started on Chapter 1, Lesson 1 of the 7th grade math curriculum. And this does not matter if you're advanced math or regular math, it's the same exact lesson for you guys today. The lesson is covering unit rates involving ratios of fractions. The course objective is going to be to have students find unit rates when one or both quantities are fractions. That's kind of ugly, but we're going to get there. They say this should take 90 minutes to do, so this is going to be broke down in 2 or 3 different videos, and it is going to be a 2-day course in class. Now, before we get into that, a couple of things I want to look at. We do have definitions. The definitions are going to be the very top of your module section for module 1. The very top line is going to be a list of all the definitions for the chapter. You need to start off by, whoop, that's the wrong course. Right there's your course. You need to start off by pausing this recording and writing down the definitions for Chapter 1, Lesson 1, which are those definitions right there. Pause, write that down, and then we will move forward from there. Did you get that done? Excellent. Now we're going to have an introduction video for this course, or for this module.
Have you ever doubled or tripled a recipe? Suppose you were making banana bread. You might need 2 cups of flour for every half cup of butter. If you double the recipe, how many cups of flour would you need? You would need 2 times 2, or 4 cups of flour. How many cups of butter would you need? You would need 2 times 1/2, or 1 cup of butter. What would you need if you tripled the recipe, quadrupled the recipe? Because the ratio between the number of cups of flour and the number of cups of butter in this recipe is always the same. 2 cups of flour for every half cup of butter. You can easily determine the quantities of each ingredient when doubling, tripling, or quadrupling the recipe. The relationship between 2 ingredients in a recipe is considered a special kind of relationship because the ratio between 2 ingredients is always the same amount. Imagine what would happen if this ratio was not the same. If you tried to triple the recipe and the ratio of flour to butter changed, your banana bread might not turn out. But it's not just in the world of cooking that you see these special kinds of relationships. In the world of fitness, many fitness club memberships charge a set amount per month. If there are no other fees, then the relationship between the cost and the number of months is the same special kind of relationship. The ratio between cost and the number of months is always the same. Why is this important? You can easily determine the cost for any number of months if you only know the cost per month. In the world of finance, exchange rates also exhibit this kind of special relationship. Suppose you wanted to convert US dollars to Japanese yen. For a given exchange rate, it doesn't matter if you convert $10 to Japanese yen or $1,000 to Japanese yen. You'll use the same rate. Why is this important? You can easily determine the amount of Japanese yen that would be equivalent for any amount of US money, if you know the exchange rate. Relationships like these are called proportional relationships. What does it mean for 2 quantities to be in a proportional relationship? Are you ready? Let's begin.
And with that, we are ready to start this lesson. So let's get started with a little warm-up problems. You guys pause the video, solve these problems, and then we're going to check and make sure your answers are correct. All this should be straight up review. Did you get it done? Let's check your answers. For the first problem, we're going to get my pen tool back here, and we're going to rewrite it using the good old keep, change, flip. Keep the first number, change the division multiplication, and flip or take the reciprocal of the second number. Simplify. Nothing simplifies here, so we're going to multiply. 2 times 4 is 8. 3 times 1 is 3. And that, of course, gave us an improper fraction. For an improper fraction, we're going to have to do the round robin, where we put the first number in the house. Let me bring that down a little bit. First number goes in the house. Second number goes outside the house. 3 goes at 8 2 times. 2 times 3 is 6, with 2 left over. So your answer, round robin, is 2 and 2/3. 2 and 2/3 for the answer of that one. For this one, we're going to make them into improper fractions first. So we're going to use the Texas approach for that part. 5 times 1 is 5, plus 3 is going to be 8 over 5 divided by 2 over 1. Then we're going to keep change flip. That's going to give me 8 over 5 times 1 over 2. Simplify. 2 goes into 2 once. 2 goes into 8 4 times. And multiply. 4 times 1 is 4. 5 times 1 is 5. And we're going to circle that answer. This one here is ready for a simple keep change flip. So we're going to do equals 7 over 8. Keep the first term. Change division multiplication. And flip or take the reciprocal of the second term. Simplify. 4 goes into 4 once. Nope, that's not what we wanted it to do. 4 goes into 8 2 times. And you multiply that out. 1 times 7 is 7. 2 times 3 is 6. And of course that one's going to be an improper fraction as well. And when you do the round robin, you're going to get 1 and 1/6 for it. Your final problem, we're going to use a Texas approach again. T and X, also known as plus and times. 6 times 3 is 18. 18 plus 5 is going to be 23 over 6. Divided by 3 times 1 is 3 plus 1 is 4 over 3. That we're going to keep change flip on. Going to give me 23 over 6 times 3 over 4. We're going to simplify. 3 goes into 3 once. 3 goes into 6 2 times. And we're going to multiply. 23 times 1 is 23. 2 times 4 is going to be 8. And when you do your round robin on it, that one will come back to the mixed number of 2 and 7/8. For the final problem, Benji buys 3 yards of fabric for $7.47. He realizes later that he's going to need 2 more yards of the same fabric. How much will the extra fabric cost? To do this, we're going to use a unit rate, where we're going to first find out what 1 yard of fabric costs. To do that, I can say, well, I know that $7.47 gives me 3 yards of fabric. I want to get 1 yard of fabric, so I'm going to divide the top and bottom by 3. 3 will go into 747. Let's see here. Let's come off to the side and do this just so y'all can see how I'm doing my problem. 3 goes into 7 2 times. 2 times 3 is 6. Bring down the 1 and the 4. 3 goes into 14. The decimal goes up 4 times. 4 times 3 is 12. Bring down the 2 and the 7. 3 goes into 27 9 times. 9 times 3 is 27 with nothing left over. That means that our fabric costs $2.49 per yard. To find out how much 2 yards is going to cost, well, we can say that I've got $2.49 for 1 yard times 2 over 2 is going to give me my 2 yards. And to find that out, we're going to do some more scratch work. 2.49 times 2. 2 times 9 is 18. 2 times 4 is 8. Plus a 1 is going to become 9. 2 times 2 is 4. Bounce, 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 bounce. So it's going to cost $4.98 for 2 yards of fabric. That is showing your work, folks. That's what I would expect to see on these problems. And now it is time to actually get into our lesson. Unit rates involving fractions. In Japan, millions of people travel between locations in bullet trains along a series of high-speed rail lines known as the Shinkansen, I guess. These trains can carry passengers from the capital, Tokyo, on the east side of the island to the ancient city of Kanazawa on the west side, a distance of 282 miles in only 2.5 hours. That's crazy fast. These are the kind of problems that we're going to be working on for this chapter. An example of how they would use it is they would say the train's rate can be written as a complex fraction where you have a whole number, 282 on the top, and in the bottom you have a fraction or a mixed number inside your fraction. Guys, I hate complex fractions, but we're going to learn how to deal with these today so that they're not so bad. Study the fraction. How does this fraction compare to other fractions you've seen? Well, you got a numerator and a denominator, and that's about it, right? What do you think it means for a fraction to be complex? Well, I just said that to you. These are the types of problems we're going to be working. We're not working this one, but we have a lot more to go with. So, how can we find a unit rate in which both quantities are going to be fractions? That's going to be our leading question here. Three friends are training for a 1-mile race. The rates are shown on the table. How long will it take Sasha to run 1 mile at her current rate? Use any method. However, you have to justify your method. You need to be able to explain why your method works and how many different ways are possible to solve this problem. How are all methods similar? Well, I think what I'm going to do is I'm going to solve this by creating a unit rate. But that's not the first way the textbook decided to do it. The textbook decided they wanted to use a bar diagram, so we will use their method first. Now remember, we got the inquiry problem here where we wanted to find out how fast Sasha was able to do 1 mile, right? And we can see in our problem that Sasha ran a 1/4 mile in 65 seconds. So, with that in mind, we're going to use a bar diagram as our first approach to solve this problem. For the bar diagram, you can see they have it broken down to where Sasha did 4 1/4 miles, and these 4 1/4 miles added up to be 1 whole mile. We also know what is going to go in each one of these spots. Well, how long did it take her to do the first 1/4 mile? That's going to be 65 seconds. The second 1/4 mile, 65 seconds. The third 1/4 mile, 65 seconds. And the fourth 1/4 mile is 65 seconds again. So, what is 4 times 65 going to be? Well, 4 times 60 is going to be 240. And there you got 245, 250, 255, 260 seconds. Let's see if that's the way they want that answer to go in. We're going to check our answer, and bingo, it'll take her 260 seconds, which incidentally is going to be 4 minutes and 20 seconds to be able to run that 1 mile. 4 minutes and 20 seconds, that's honking fast, guys. I mean, that's really moving for a 1 mile run. Now, let's move forward from there and see what else we have. They say you could also use scaling to find Sasha's unit rate. Solve this problem using scaling, you must be able to explain why your method works still. So let's look at this using scaling. Now the textbook didn't show us how to use scaling on this, so I'm going to show you how I would do this. For scaling, the general idea behind it, let me get my cursor back where it belongs. The general idea behind it is you set up a ratio where you have got the 65 seconds and the 1 1/4 mile. And then you ask yourself, what could I multiply the top and bottom by so that my bottom number is going to equal to 1? And the answer to that is going to be 4. 1/4 times 4 is equal to 1 whole, and then you'd have the 65 times 4, which is going to be 240. So right there, of course, you need your unit rates. You're going to have seconds here, you're going to have miles here, you're going to have seconds here, and miles here. You've got to carry your units through it, and you would get the same answer of 240 seconds in 1 mile that we came up with. Actually, not 240, my bad, that should be 260 seconds in 1 mile that we came up with when we worked the problem the other way. Now, how does the problem using a bar diagram relate to the problem using scaling? Which method do you prefer? Stop and pause the recording, write down your answer, and then we submit it, and we will look at some sample answers after that. Now what I wrote was that in both methods you had to multiply both the time and the distance by 4 in order to get to the final answers. I'm going to click done here. Sure, I'm done. Yes, I am. And then we got some sample answers. They said both methods arrive at the correct unit rate. Drawing a bar diagram helps me to visualize the problem. Wow, it may be faster to use scaling. I definitely prefer scaling over using the bar diagram. So now we got some more. If Pedro and Emily each continued running at the same rate, how long will it take each of them to run 1 mile? You get to use any method you want, but you must be able to justify your answer. And what you're going to do is you're going to solve each of them, and when you solve them, you're going to put your answers in here, and here they got it set up for you to solve it using the bar diagram. So you guys take and pause the recording, fill in the blanks on the bar diagram, and then we will go over it. Did you get it done? Well, all right, let's take a look here. Pedro, we know, ran 2/3 of a mile in 240 seconds. So we're going to take and say half of 2/3 was 1/3. You got the 2 1/3 sections there. And half of 240 seconds is going to be 120 seconds. So I'm going to take and write 120 in each of those. Meanwhile, we have Emily ran 5/6 of a mile in 275 seconds. You can see that right there. So we're going to take that information and say, all right, so if it took her 576 seconds, or 575 seconds to run 5/6 of a mile, how much did 1/6 of a mile take? And to answer that, we would have to divide 275 by the 1, 2, 3, 4, 5 sections. And when we did that, I'm pretty sure the answer would be 55 in each one of those sections. And when we check that, we're going to find out that yes, we got both of those correct. Now, the last step for this process is how can you find the unit rate in which one or both quantities are fractions? You need to take and pause the recording and then answer your question, submit your question, and then we're going to look at a sample answer. Alright, here's the answer I submitted. I said to find a unit rate, you need to divide both parts of a fraction by the denominator. I'm going to click done, and then I'm going to say, well, what's the sample answer? They said I can draw a bar diagram or use scaling to help me find a unit rate that involves ratios or fractions. That's the two methods that they showed today. I mentioned a third, which we will be talking about later. Now that's going to be the end of part 1. When we come back in part 2, we're going to work on this problem, which looks like we have buckets of water and a cup of water. I wonder how we're going to use those. I will see you in part 2.